start at the material. So actually, we're going to start with this slide. So if you find this slide, yeah, you can keep those. So if you find this slide, this is where we're going to start. But the reason I brought in the review slide is to kind of remind you, when we're talking about humidity, different ways of expressing water vapor in the atmosphere. Okay. Yep, okay, cool. It was on page 5. Very good. Okay, so page 5. Again, this is a review slide because, everything we covered Friday potentially could be on the test. And actually, this subject kind of links into what we talked about on Friday. So, if you're a visual person, there's a lot of things in physical science that, to me, are just scream visual, okay? If you're a visual person, hopefully you can kind of think of gas particles as being really real live entities. And you guys told me that mostly the gas in the atmosphere is nitrogen, okay? So it's 80-20, 80% nitrogen, 20% oxygen. And then those cute little Mickey Mouse things are water molecules, okay? And they are ramming around in this room too. Here in a minute, actually, I've got a gizmo. It's not a gizmo. But we've got a way actually to measure the water in this room, which is kind of cool. And all this is, each one of these will do it for you. There are 2 thermometers. One has what we call a cute little sock, and the other thermometer does not. Is that not adorable? Mm-hmm. Okay, so this will tell us how much water is in the room. So we talked on Friday kind of about the math part. These first 2 are ratios, absolute humidity and mixing ratio. Okay, so you might want to just kind of go back and look at those if you need to. But vapor pressure to me is basically kind of at the top of the figures. Some of the figures we looked at, they had that cute little pressure gauge. That's kind of measuring water vapor pressure. Okay, relative humidity is what you're basically have been recording, and it's the amount of water vapor there divided by the amount of water from the table that it needs to be to reach saturation at that particular temperature. Okay, so here we go. Dew point temperature. Oh my gosh. So my husband got up this morning and he looked at the Roku screen, which just kind of bounces the temperature and humidity outside. And he's like, oh, 100% humidity. I bet there's some fog. And there wasn't in Burlington, but oh my gosh, there was between here and Burlington. It was terrible. Okay? So the fog, you definitely can get fog at 100% relative humidity. Mm-hmm. The other thing, while I'm thinking of it, I'm going to digress a minute. I bet you're okay with this. We've got time. I'm going to take you out to the internet right quick. Okay. So this is, remember what these columns are. Okay, they're just a busy sort of little screen. But this column right here, actually, you do have access to it's like, of course, homepage is the rightmost column. This is just my Twitter feed, okay? But if you were out and about this morning, like I was, about 8:30, fog, it was definitely how we had fog. And if you looked over at the trees, did you see them with a nice, thick, white coating? Just beautiful. You're like, I told somebody it's fancy frost is what it looked like.
In Montrose, you couldn't see anything but white.
It was very foggy this morning. But if you look closer at that fancy frost, actually there's 2 possibilities, and I chased it down. I didn't know until this morning, but something's called hoarfrost, and there's also something called rime, R-I-M-E. And to me, they're very similar. When I was driving down in the fog, did you guys notice the temperature was running about 22 degrees Fahrenheit? So you're like, dude, that's like freezing. It's kind of cool, no pun intended. Those little particles that was making it hard for us to see, visibility was limited due to those particles, that cloud we were driving through with the fog. So they could have been most likely what we call supercooled liquid water. So it's water that's in this liquid state at 22 degrees Fahrenheit. You're like, 22 degrees Fahrenheit should be frozen. No, it's super cool. We'll be talking more about that. But what that can actually do, fog like that can create this cool frost. That's my only point. I just think that is so cool. So there's some frost. And what this author tries to do is talk about the two. And again, I posted it. It's just beautiful. You know? And she differentiates that. Up there was hoarfrost. This is rime, R-I-M-E. They're very kind of similar. See? Isn't that not beautiful? Thank you, Kathy Bell. The other thing, it doesn't have to do with today's lecture, but just hang on. I posted this too. Saturday, we had a little bit of precipitation, right? Was it Saturday into Sunday? I don't know. But if you looked at it, it was snowflakes. But sometimes it was like these. It was like, let's see.
Especially at first, it kind of started out like this, very fine, or hard.
Yeah,
pellets.
hard pellets. Yeah, and so sometimes, and I'm hoping when you're done with this class, you'll know that it cannot hail. It cannot hail this time of the year. It will not hail. Okay, that's crazy. But we could get sleet. Sleet is a different phenomenon than hail. And actually, what I'm going to pull up is a picture of grapple. Grapple, G-R-A-U-P-E-L. Okay. So to me, this is what it looked like. The stuff, it sounded kind of hard. Like this is a good picture.
Yeah, even if you look at the ground, you could see like little.
Yeah, exactly. Totally. And this article that I posted on Twitter, I like it because this explains why we have grapple. Okay? Oops, come back. So I know this is like really looks really busy, but it starts out as snow. See this red right here? That's where it's going to melt. It's like the melting region. Okay? So it starts out as snow. It melts, or some of it partially melts. It kind of flattens out the cute little fluffy flake, and then it refreezes, okay? And you can get sleet that way, okay? But you can also get just kind of a melted snowflake, which is grapple. I just think that was so cool. I also thought about you guys, and if anybody in here is doing their photo journal, photo things, I hope you have snow now, because that's it. No more snow. Stop hoping for snow. If it's you, stop it, okay? So, dew point temperature is the temperature at which the air needs to cool down in order for it to reach 100% relative humidity. That's the dew point temperature, and I think we kind of talked about that earlier. But here's kind of a poor man's sort of humidity measuring device. Okay, if you have like a cold beverage, and if the air has water vapor, if it's relatively humid, okay, what can happen is in the vicinity of your cold beverage, you cool it down to the dew point temperature. So what condensation is on the outside of your glass is basically water vapor that's condensed. But you know how they say like Arizona is hot, but it's a dry heat? Okay, so you take the same mug down to Arizona, low humidity, okay, and it's not going to sweat. How fun is that? Okay. So if it sweats, or if it doesn't sweat, or how much it sweats, it's an indication of the water vapor you have going on. Okay? So I think that's kind of neat. So in general, if you, and I think I might have mentioned this before, if you go to bed at night and the current temperature is like within, let's see, how's that go? Well, this is a different thing. But if you don't have to drop very far in order to reach your dew point temperature, then you could go ahead and have condensation happen. You could have fog, or you could have dew, or you could have frost. But what this is saying is if your dew point temperature is really high, 75, that's pretty high, that means your real temperature has got to be higher than that, because dew point temperatures are always lower than your real temperature. Okay, so that means that actually it's pretty humid. If your dew point temperature is really low, like 10 degrees, then that means it's really dry. Okay? That'd be more like a frost point temperature, but it's really, really dry. All right, so here's a map to just kind of, and it's probably not so surprising, along the Gulf, okay, along the coasts. Oh, Okay, the blue means that they generally have high dew point temperatures, which again, high dew point temperatures means that you don't have to lower very much before you can have condensation occur. So let's see. I see you nodding. So there's Iowa. I'm so bad with my maps. So is that North and South Dakota? And then is this Nebraska, and this Kansas. Oh, yay. Okay. So Kansas kind of has a spread of kind of just general. I mean, this is just a ballpark. What sort of dew point temperature they're looking at. Iowa, yeah. We have kind of a spread too, but yeah. Okay, so the higher the dew point temperature, the higher the humidity. Okay.
I always notice the dew point's higher near rivers because the moisture off the river.
Yeah, that makes sense.
Like it usually snows first near rivers.
Mm-hmm. Yep, I agree. So we're going to talk about how do you measure humidity. And remember, I brought these in, so we're going to measure the humidity in this room momentarily. Okay, but but a device used to measure humidity we generally call a hygrometer. Hygrometer. This that I brought actually is a type of psychrometer. It's a Sling psychrometer. The whole hair thing, actually, here's a picture of the hair thing. And my hair's not naturally curly, but the whole hair curls different in humidity or dry conditions. Mm-hmm. Yeah. So actually, and I don't think, this could be, is this human hair? Horse's hair. Okay. But basically, it will expand and contract based upon its curliness that's responding to the humidity. And then this barrel, remember we talked about barrels that you can wind them up and they kind of go around? Okay, so actually it goes around and then the needle moves up and down depending upon what the hair does. So hair can have The other one, electric hygrometers. I kind of brought in pictures from, a couple pictures from the internet. Kind of some interesting techniques there. But what I want to look a little more closely at is the psychrometer. And I brought these are Sling psychrometers. Okay, I don't think I have enough. I have enough for each row. So the way they work, you guys are so the way it works is I'm going to come around, and the one that's wetted, I ran out of them. The one that's got a little sock, we're actually going to wet. Okay. So the way Sling psychrometers work is you wet one, okay, and the other one's dry. Now it says that you're going to ventilate them. Yeah, I see some of you slinging them. That's how you're going to ventilate them. Okay, the Sling and Sling psychrometer is just about getting air to it. Okay. Now one of the things you guys know is that, and we talked about this before. Okay, I went on to the next slide. Careful, no slicing and dicing, people. Went on to the next slide, but. We talked about, I think, a little bit about the heat index, and we said the heat index feels like temperature actually has to do with if it's humid outside and the temperatures are high. If the temperatures are high, we're going to sweat. And if it's humid, our sweat's not going to evaporate. Okay, we kind of talked about that, and this is a similar phenomenon. Now, why do we want our sweat to evaporate? Because we want it to cool us off. So actually, if you get something, we're going to wet your sock here in a minute, and after you sling it around, if you were to put your fingers on your wet sock, it'd be cooler. It actually is going to be cooler. It's going to have a cooling effect for the thermometer that it's around. Okay? So depending upon how much water vapor there is already in the air, again, okay, if it's already muggy in here, it's not going to have much of a cooling effect. If it's dry in here, it's going to have a crazy high cooling effect. So that's kind of how it works. All right, and then we'll look at it on a temperature, or on a table. So here we go. So just your wet one. Swing it around. Thanks, ma'am. And then then once I give it to you, go ahead and swing it around, let's count to 30. And then jot down what both temperatures say, and then I'm gonna ask you what the temperatures say.
Come on, you do the same thing.
Yeah, I'm watching.
Swing it around.
Swing it around,
You
count
can
to
do
30 or
it.
so, and then jot down what the temperatures say.
Getting hit by water. Yeah, you're supposed to. For 30 seconds?
I like when you know. Very good. Go, Nancy.
Oh, what is this?
So we're gonna dip this one. This is the soft one. We're gonna wet it, and then you're gonna swing it around for 30 seconds or so, and tell me what the temperatures are.
Okay. Oh.
Okay,
And it's a hard temperature scale to read, I think.
She told me.
well, either way, it's gonna take you.
So then I'm gonna go around, I'm gonna start with K and go around, and you're supposed to tell me two temperatures. And
And with the other one, do it.
let's go with the dry one first,
Yeah.
and then the wet one.
Fine.
Ooh, I found it.
I don't know. No.
That one's dry.
Got 'em up.
Oh, it is cold.
Is it cold?
Yay, so cool.
Okay.
Kind of stung my finger.
Okay,
Has it been 30 seconds?
yes.
Okay, wrong one. There you go.
14
14.
precise 14.3.
Kay's looking at her temperatures.
24.3. Dry, 24.
Okay, what do you think, Kay? So we're gonna go dry and then wet.
This is way too fun.
23 and 14.
23 degrees Celsius. Whoa, great.
Problemo.
Okay, I'm gonna actually add another column, and I'm gonna put depression. So that's a little subtraction. So let's see. I got 9 degrees. That's a hard one to beat. They're all gonna be a little bit different. What you guys?
Dry was 22 and wet was 13.
Oh, wow.
So almost
Dang. So what's that? That's 9 also? Woohoo! Awesome.
Dry was 22 and wet was 16.
16. Perfect. That's 6. Awesome. What'd you guys get?
Dry was 24 and then wet was
18. All right. You know what we might be seeing is actually this is I'm going back towards the window. So this is the window and this is the front. Because I wondered about that. We'll have to see with the other guys. So you guys got a 6 degree also? Awesome.
I'm gonna mess that up. My dry was 23 and my wet was 15.
23. 15? Oh, well, now you're kind of over here in the corner. Let's see. So, wow, yeah, that's 8. Thank you. Okay, what you got?
All right, let's see. For dry, I have what is that? 23, 25?
Let's see. I'm like in 20, 22 maybe?
I don't know. 22.
Uh-huh.
Okay. And then
Oh, that's true.
Wow. Okay, so that's 10, maybe 12?
Yeah.
Wow. Okay.
You don't look at it.
All right.
I did that.
Now, I wonder sometimes if some of us are better at swinging than others. But it should kind of level out at a constant depression. Okay. And what did you guys get?
For dry, we got 22.3. And wet, we got 14.3
22.3?
for dry. And wet, 14.3.
See, they threw me off because they went with that's good. They went with the fraction of it. So that's,
Really, you broke it.
is that 8? Wait, yeah,
See.
8 degrees Celsius. That's okay. They're getting kind of brittle. As long as the glass didn't break, right? Okay, that's okay. The plastic's brittle. You're fine, Lily. Okay, so let's take a look at this, all right? So yeah, I'm not sure we necessarily had, I don't know. You know, when you gather data like this, you're like, is this real or is it an artifact? You know, is it really, where you have a greater depression, that's actually where it's drier. I'd buy that. And where there's less of a depression, it's actually, you have less evaporation because it's more humid. Okay, so just for purposes of looking at a table, I'm going to go ahead and go with, I'm going to make a decision here when I decide. I'm going to take these collectively and probably round them to, what do you think, 22? No, 23. Maybe 23 seems like the, we'll go with 23, and we're going to find these on a table here in a minute. 23 degrees Celsius is going to be our dry, and our wet, let's go with, Where's Glenn when I need him? 15? That's what I was trying to think of.
Down in this classroom.
Okay, let's go with 15 degrees Celsius. So here in a minute, we're going to look at dry temperature, 23 degrees Celsius, wet bulb temperature, 15 degrees Celsius. Wow. Okay, so this is actually what you guys did. It's a Sling psychrometer. The Sling part is just the ventilation. And you had two, this is like, it cuts off. Isn't that a weird graphic? There's no like little thingy there. But anyway, you got it wet and you slung it around. Okay. Here's the table I was talking about. So let's see if we can find our two temperatures. So our dry bulb temperature is kind of along the y-axis over here. And we decided to go with 23. All right, so I don't see a 23, so we'll kind of slip, well, let's round to 24, or 22, excuse me. And then we'll see where it intersects with our dry bulb. This is actually our depression. So remember that third column? Basically, we need to subtract, so help me out. What is 23 minus 15? Thank you. It was an early morning. So along the x up there, we're going to find 8 and see where it intersects with 22, okay? So here's 8. And if you're like me, I almost need something flat to kind of find that is, yeah. Okay, now this one actually is the dew point temperature. So we would need to, the air has the humidity such that we would need to cool the air down from 22 degrees Celsius to 8 degrees Celsius, which is not freezing, right? 0 degrees Celsius freezing, in order for to reach 100% relative humidity, to slime up the place, okay, to basically get, remember if you get 100% relative humidity, condensation occurs. So that's how it works. So let's look at the next one. It's kind of similar. Again, let's stick with 22 over here for our dry bulb temperature. And we'll go with 8 for our depression. Now this one reads a slightly different characteristic. Okay. Yeah. So you know when you guys have been doing your weather logs and the column that says for the percent relative humidity, that's what the percent relative humidity in this room is. It's about 40%. Which remember in the winter time where the school is, or any building you're in, is cycling cold, relatively dry air from outside into the room. Okay, so that's why we need to humidify this room. 40%. All right. So I think, is this a repeat slide? You guys don't have this slide next, do you? This is another repeat slide because I wanted to remind you of one of the things that we've talked about in here. And you guys may have even known this intuitively before you took this class. If you want to go ahead and have something condensed, you can either cool that chunk of air down, okay? You can lower the temperature, or you can take that chunk of air and somehow infuse it with more water vapor to reach saturation. Those are your two choices. Now, we're going to spend a little bit of time. I'm going to introduce you to something kind of important in meteorology. This whole idea of a chunk of air. Well, we kind of talked about chunks of air before. We'll call them parcels of air, okay? And we're going to actually focus on taking that chunk of air and cooling it down. So, so this slide, now you do have this slide. So a few slides ago, when we talked about relative humidity, we took this chunk of air and we made it go up, and the chunk of air got bigger, just like a weather balloon. And you can think of it, I think the reason it gets bigger is basically that air is thinner up there. That chunk of air has gas particles that have a certain pressure exerted against the edges of that parcel of air. It's weird to think of a parcel of air really has an invisible boundary, but that's kind of what we do here. Okay, so the chunk of air will get larger. Okay. So if you buy that, here we go. As a chunk of air gets larger, one of the basic things in understanding about actually cloud formation, which what is a cloud? A cloud is basically
Condensed.
water vapor has condensed, yeah. So basically if you get a chunk of air rising and expanding, it will cool down. And it can cool down and create your clouds. That's it. That's it. Okay? So there are different ways to create clouds, but this idea of a chunk of air rising and expanding to cool down to the dew point temperature for condensation to begin, to create your liquid water particles, or heaven forbid, ice particles, okay, that's kind of the way clouds are formed, okay? So expansion is the biggest way to go ahead and get clouds to start to form. So we're going to kind of talk about that a little bit. So rise, expand, cool. Okay. So I've been kind of talking about this chunk of air, we call it parcel of air, that has kind of an invisible boundary. It's just, you know, it's kind of, anyway, has an invisible boundary. So we have two options with regard to anything if you want to add heat to it. One is to diabatically heat it. And with a diabatic process, basically you take your system, could be your chunk of air, and you, from the outside, add heat in. If you go to heat up a pan of water, okay, basically you put your pan on the stove and you go ahead and from outside your system, which is your pan of water, you go ahead and heat it up. That's diabatic heating. Okay, an adiabatic process or an adiabatic heating or adiabatic cooling is basically you go ahead and define your system, which we're going to be a chunk of air, and any sort of, it's kind of like what happens in Vegas stays in Vegas sort of thing. So any occurrence that happens within that, I should say nothing crosses the boundaries. Okay, it's an adiabatic process. Okay, so we have diabatic where stuff crosses your invisible boundary or your real boundary. Then we have adiabatic where whatever happens is just inside. And this idea of a chunk of air expanding and cooling, and I'll talk about why it cools as it expands. Okay, that actually is adiabatic. Why? Because it's only happening within that chunk of air. Okay. This idea, when I first started teaching this concept of diabatic versus adiabatic, when I first started teaching meteorology, I was like, now how does that work? I'm like, oh, that's how that works. Okay. We do a lot of diabatic things, but this is adiabatic, actually going to be cooling. So why does it cool? Well, it's the law of the universe. Okay, the universe says, if you do any work, thou shalt fund the work. Fund as in F-U-N-D. Okay. So making something larger, like the chunk of air getting larger, that actually is work. Work is done, and thou shalt not do work without paying for it. Okay. So who pays for it? Well, it's a diabatic process, so basically the little molecules inside the parcel pay for it. And they go slower. They pay for it by their kinetic energy. Okay, it's kind of a trade-off. In order for it to get larger, they gotta go slower. They gotta cool down. That's basically how it does. So it's funded at the expense of the thermal energy of the little cute little particles inside the parcel as it expands. It's an adiabatic cooling process. Now you might be like, oh, I don't think I could explain all of that on a test. Well, hopefully you can talk about the expansion and cooling, even if you don't buy how it happens. And you can talk about adiabatic just kind of happening within the parcel versus diabatic from outside. Okay, so a chunk of air rising will expand. That expansion is work. That work needs to be funded by something, and it's funded by the cute little particles inside the parcel. Okay? Adiabatic cooling. All right. So do you guys remember on your, well, just the other day, when you guys took your test, to prepare for your test, you guys memorized war. You're like, more. Okay, oh, no you didn't. Hold on. ELR. That's better. You guys memorize that. You didn't memorize more yet, but you will for the next one.
What's that?
Okay, environmental lapse rate. Basically, if this is my Earth's surface, if you go up 1 kilometer, it's going to cool 6.5 degrees Celsius. Yep. So let's say it starts at 10 degrees Celsius, it goes up to 1 kilometer, and it must be, what, 3.5 degrees Celsius? Okay, I think I'm good with that. And then it cools another kilometer, so let's see. Thank you. Negative 3.0, exactly. Goes up one more, negative 9.5. Okay, exactly. Are we good with that? Cool. This actually is what we call the environmental lapse rate. You go up. Well, I'm going to I'm going to introduce another rate. Okay? And it actually is called the DAR, D-A-R. Oh. Does anybody see the... Okay. So according to the dry adiabatic rate, so I'll put that 6.5 degrees Celsius per kilometer. Now, let me go ahead and say on Wednesday, I hope you guys don't get mad, because on Wednesday we're going to change up. Remember, this is like if you send up, this is my weather balloon. If you send up a weather balloon with a little measuring device, this is kind of what you're going to see, how the temperature cools. But I'm here to tell you that this is not in stone by any means, okay? I will say this varies, and actually we're going to vary it on Wednesday. Now, this other down over here, if you take a chunk of air and let it rise, it's going to get bigger and bigger and bigger. And the chunk of air is going to cool down, not the environment, okay? And it's going to cool down 10 degrees Celsius per 1 kilometer. So if it starts out at 10 degrees Celsius, it's going to be at 0 degrees Celsius, the chunk of air. And that's going to be at negative 10 degrees Celsius. If these were each 1 kilometer, up here it'd be really big, and it'd be minus 20 degrees Celsius. Get that? That's all this slide is talking about. Okay. So here's our chunk of air. It's not at 0, but it's at 32. See the parcel? I like the figures in this textbook. There's your parcel of interest. It's going to go up and get bigger. How much is it going to cool? Well, if that hash mark is 1 kilometer, it's going to cool 10 degrees. Okay. So this is your dry adiabatic rate. So at the top of this one, if you want to go ahead and put DAR, exclamation point, you can, because we're going to abbreviate it with those 3 letters. The DAR does not vary, it's constant.
Why is the DAR different from the ELR?
The ELR is the environment.
Okay, so it's just everything. The DAR
Yeah.
is just a parcel.
And actually, this is the parcel. Yep.
Okay.
And we get this from a weather balloon, and this is in stone. This is
So
constant.
when you have
This
2
one.
parcels of air that start at the bottom and they get bigger and bigger, do they just mesh?
They could. Yep, they could. Mesh. So it's going to cool another 10 and another 10. Okay. So actually, as it goes up, we call that adiabatic cooling. That is adiabatic cooling. Dry adiabatic rate, adiabatic cooling. Chunk of air. Only within the chunk of air. And actually, it's a player in weather, and we'll probably be talking about it a little bit. But if you can get that chunk of air to go down, guess what? It's going to get smaller, and it's not going to do work. Work is going to be done on it. So if you can get a chunk of air to go down, actually it's going to warm. The big thing with a chunk of air going down is actually on the leeward side of a mountain. As a chunk of air goes down, okay, it gets warm. So oftentimes we see on the leeward side of mountains these dry, hot conditions. Desert. Okay. So very good. So that's that's a good place to stop. So hopefully you guys put DAR at the top of this. And then we'll pick up on Wednesday. I do.
Is that the
Would you like it? What's that?
What's it